Markov chains. This section we discuss how to apply matrix theory to solving problems of probability that involve what is called stochastic mathematics, here stochastic matrix theory. This is the concept where if you have various sets, and these sets are called states, certain moments in time, such that by applying a particular matrix operation, here matrix multiplication, we can move the initial state to the next state. The states could be in terms of weeks, days, months, years, whatever the time frame that may be given by the supplier. So we discuss the probability theory with a matrix such that each entry in the matrix is said to be a probability. Probabilities are said to be numbers between 0 and 1, where if we are given a particular state, you should supposed to be able to add up all of the entries in that state to give you 1. So all of the probabilities must sum to equal 1. Well, here we talk about three things with the idea of Markov chains. That is, we want to be able to solve a Markov chain, discuss the nth state, see if we can find that. Secondly, does the Markov chain achieve what is called a steady state? That is, after so many iterations of the transition of the Markov chain, you keep on getting the same matrix. If that is the case, then the Markov chain is said to reach its limit. Can we find it? And then lastly, if we have a steady state matrix, or if we have a Markov chain for that matter, can we find the steady state matrix of what is called an absorbing Markov chain? So first, let's just deal with some basic definitions. Stochastic matrices and the idea of a Markov chain. Many types of applications involve a finite set of states. Here these states are said to be S1 all the way to S sub n. For the matrix, the state would actually represent the column. So each column in the matrix represents a states. When you produce the so-called matrix here, this is the matrix P. It's the transition matrix of probabilities. Each column, since each entry is said to be a probability, probabilities exist between 0 and 1. So each entry in the so-called matrix has to be an entry between 0 and 1. What makes this matrix, the so-called transition matrix, what makes it a Markov chain? Well, we define that the sum of each column must equal to 1. Now that's the definition for any probability state, especially as we apply this to a matrix, that the sum of the column must add up to give us 1. Well, let's discuss in terms of what makes it a so-called Markov chain, and what is that, and a little bit more about the idea of stochastic matrices. At each transition, each member in a given state must either stay in that state or change to another state. Here we build the concept of stochastic matrices and stochastic mathematics. For probabilities, this means that the sum of the entries in any column of P must be 1. And so if you take a column here, we add these entries up, and those entries should add up to 1. Such a matrix is called stochastic. Here, the idea of a conjecture, which simply says there's a question that needs to be answered. So this transition matrix P is called a stochastic matrix when each entry is a number between 0 and 1 inclusive, and the sum of the entries in each column of P is 1. So basically this stochastic matrix is just a probability matrix. That's all we're saying. The nth state matrix of a so-called Markov chain. Here the idea of a Markov chain is that if we take the so-called transition matrix, and if we find the so-called next state, here we have some initial state x sub 0, we can find the next state x sub 1, and then likewise we can find x sub 2, because that would be p to the second, or p raised to the second power times x sub 0. We can continue in that state. X sub 3 is p to the third times x naught. Now, there's another way that we can deal with this, and that is you can look at x sub 2 as actually being here this matrix x sub naught times p, and that's fine. You can do that. So this is p times x sub 1, where you recall that this was no more than p times x naught. So thus we get p squared times x naught. Well, we continue in this fashion until we build the case that x sub n is equal to p to the n times x naught. This chain sequence is simply called the Markov chain. So we can continue in this process, and each of these states is said to produce a chain. Here, the Markov chain. Well, let's take a problem without further ado. I will encourage you to do what I do, and that is, for these problems, I am using a graphing calculator, and I would encourage you to use a graphing calculator to do this particular section. And even for the exam, I will allow you to also to use a graphing calculator. It just makes life a whole lot easier. So here they want us to find x sub 1, x sub 2, and also x sub 3. So x sub 1 is simply this transition matrix P times x naught. Now, what I did was, on my graphing utility, I put this operation in, and that gave me the result. And so that kind of helps us cut down on the work. And so multiplying this out, remember that this is a 3 by 3 and this is a 3 by 1. So the result would be another 3 by 1. So we get 0.16, 0.18, and then 0.66. Now it says to find the next state. Well, x sub 2 is simply going to be that same P matrix raised to the second power times the initial state. And so again, on the my graphing calculator, I plug this information in. And so for this one, you get, and I'll just put the information in. Now, I'm showing you my side with the answers there, but I have to still work it out and get what I get, because these days you can't trust anyone. WebAssign, or even me, you want to work it out and see it for yourself. So for the next one here, this is this x to the third is just p raised to the third times x naught. And again, you just put the matrix in your calculator, raise the power times x naught, and you get the desired result. Now, I hope you can see this. These problems correspond to the same problems for the homework there in WebAssign. An airplane has 40 airplanes in Los Angeles, 24 airplanes in St. Louis, 16 airplanes in Dallas. During an 8-hour period, 20% of the planes in Los Angeles fly to St. Louis and 10% fly to Dallas. Of the planes in St. Louis, 25% fly to Los Angeles and 50% fly to Dallas. Of the planes in Dallas, 12.5% fly to Los Angeles and 50% fly to St. Louis. And so the question is, what the heck is going on? No, that's not the question. The question is, how many planes are in each city after 8 hours? Or my wife's answer, who cares, right? Well, she's not taking this class. So anyway, we're going to just draw 3 diagrams, see if we can draw this out, and then from there we'll build the matrix, the transition matrix. And I'll show you that when you build the matrix, the entries above, looking at the column, is said to be the input, and then the rows would be the output. So first, I think to see it, we need to draw it out. So I'm going to have 3 bubbles, one for each city. So let's say this is LA. Let's call this St. Louis. And then one bubble here for Dallas. So of the airline has 40 planes in Los Angeles. This is like the initial state, right? And so we can note that. So X naught would be 40 planes in Los Angeles, 24 planes in St. Louis, and then 16 planes in Dallas. So I'm just going to say LA here just to note, and then St. Louis, and then Dallas. Okay, so that's our initial state. So now let's see if we can connect these bubbles. 20% of the planes in St. Louis fly to, in Los Angeles fly to St. Louis. I guess it'll really help if I could read, right? So we're going to say 20% or 0.2. Remember the percentages or decimals, and so these are probabilities. And then from Los Angeles, 10% fly to Dallas. Now, of the planes in St. Louis, 25% go to Los Angeles, and 50% fly to Dallas. This feels better with a 0 in front of the decimal. That's from my old teacher from Selma, Mr. Grover Bates. And then it says, looking at from St. Louis, 25 fly to Los Angeles, I got that percent, and then 50% fly to Dallas. Of the planes in Dallas, 12.5 fly to Los Angeles. So here, 0.125. And then 50% of the planes from Dallas fly back into St. Louis. Okay. So we're going to build this transition matrix now. So matrix P looks like, so here for this first column, I'm going to have LA. The columns, the order has to match the order declension here for the initial state. So I have LA first, St. Louis, and then Dallas. And so this would be the input, and over here we have this first row is LA, second row St. Louis, and then the third row is Dallas, and this would be the output. So from, when it says of, or that means so from, so here, so from LA goes to St. Louis, that's 0.2. So here, that's 0.2. And then LA goes to Dallas, that's 0.1. Right? Now this is going to be a Markov chain, as we define what's called the stochastic matrix. Is basically, just for us, for me, is just a probability matrix, which means that each column must add to 1. So once you look at, and I'm gonna go through the whole thing. I'm gonna leave something blank, and then we'll come back and fill it in. But how do you fill in what's missing? It's just 1 minus the sum of whatever you have there, and that gives you the missing link. So now let's move to St. Louis. So from St. Louis to LA, St. Louis to LA. I'm missing my L. St. Louis to LA. That's 0.25. St. Louis to Dallas, 0.5. And then from Dallas, we look at there, from Dallas to LA, that's 0.125. Dallas to LA is 0.125, and then Dallas to St. Louis is 0.5. Okay, so what do we have? Well, if you look at that, if I notice I'm missing one item in each column. If you add up the first column for LA, I have 0.3, but the total has to be 1. So 1 minus 0.3 is 0.7. So if you add up these terms in the second column, we get 0.75. So 1 minus 0.75 is 0.25. And then here, we add these two terms up, we get 0.625, and so 1 minus that is 0.375. Okay? And so then it says how many planes are in each city after 8 hours. Well, the whole time frame is an 8-hour period. Right? It says during an 8-hour period. That's what you start with, and that's what you end with. So that's just the next state, which is equal to P times X naught. So that's this first matrix, 0.7, 0.25, 0.125, 0.2, 0.25, 0.5, 0.1, 0.5, 0.375 times the initial state, 40, 24, and 16. Now when you multiply that out, and I did that, the matrix multiplication on my calculator, so I get 36, 22, and 22. So after 8 hours, there are 36 airplanes left in LA. And then for St. Louis, there are 22 planes, and then for Dallas, 22 planes. Okay. Now this next one, and they all work and they build on that same idea. So the market research department at a manufacturing plant determines that 50% of the people who purchase the plant's product during any month will not purchase it the next month. On the other hand, 40% of the people who do not purchase the product during any month will purchase it the next month. So basically what we have is those who purchase versus those who don't purchase. So we use that to build this scheme. So we have those who purchase. I guess the red on the white looks better. And here, those who just say not purchase. So here determines that 50% of the people who purchase the plant's product during any month will not purchase it in the next month. So the 0.5 there. And then it says, on the other hand, 40% of the people who do not purchase the product during any month will purchase it the next month. So 0.4. So we build now the transition matrix P. So we have those who purchase, and those who do not purchase. Now this is like from, and this is to. So those who purchase, those who do not purchase. It's from. So for those who purchase to don't purchase, that's 0.5, and those who do not purchase to purchasing, that's 0.4. Now from there we can fill in the rest since we're looking at the columns. So this has to be 0.5. When I add up 0.5 plus 0.5, I get 1, and this has to be 0.6. Now the other thing we need is the initial state. So let's look at that in terms of how many people. It says in a population of 1,000 people, 200 people purchased the product this month. So within that same month, 800 people did not purchase. This is the first month, remember. And so, since we're talking about months, so x of 1 would be the next month. So that's going to be the p times the x, 0.5, 0.5, 0.4, 0.6, and this is times 200 and 800, and on my graphing utility, I get 420, and here 580. Now they don't ask for who didn't purchase within the next month. The question was how many will purchase the product next month, and also in 2 months. So you're actually finding more than what they're asking for, but that's fine, because here all they're asking for is this number here, right? And then to find what happens, this is part A. So to find part B, you just raise p to the second power. And so you do that again on your graphing utility, and that's 442 and 558. And again, that's how my English teacher used to say again and again. They were so proper. All you need there is that 442. Well, let's look at another one. And I think after a while, you kind of start to get it, and then you get comfortable with it, and that's the good thing. So here, in a population of 10,000 people, there are 5,000 non-smokers, 2,500 smokers of 1 pack or less per day, and 2,500 smokers of more than 1 pack here per day. So it says during any month. Okay, we get to that. It looks like we have 3 sets. We have the set of it's the non-smokers, then we have a set of the smokers who smoke 1 pack or less a day, and then you have the set that smoke what is that? More than 1 pack. So let's label these 3 sets. I want to say NS for non-smokers, and then let's say here for those who smoke a pack or less. And then those who smoke more than 1 pack. All right. So it says during any month there is an 8% probability that a non-smoker will begin smoking a pack or less. So it's a non-smoker going to a pack or less, that's 0.08. And a 4% probability that a non-smoker, let me pause and tell you this. When I was in college, I took all these probability courses and stats courses. A lot of that stuff was kind of tricky. You had to kind of really hold your head up right to work that. I did realize I took more linear algebra courses, and linear algebra breaks into other departments, and I took several of those, I guess almost like Markov chain, right? Took different chains of subcategories of linear algebra. Anytime we can take any type of system and represent it with a matrix, it just makes life a whole lot easier. And let me tell you something, solving probability theory without the matrix can be very tricky. There you have a lot of what's called conditional probability. They use sophisticated formulas. One is Bayes' theorem and all of this stuff. What we're doing here with the matrix, you will, if you take any of the higher probabilities stats courses a little bit later, you will see where the Markov chains, this application is so useful. Okay, let's get back. So the non-smokers, 4% probability that the non-smoker will begin smoking more than one pack a day. So that's here, that's 0.04. For smokers who smoke a pack or less a day, so we're here, 10% probability that they may quit. That's good. So we got 10% chance. And then a 10% probability that they would increase. And then for smokers who smoke more than one pack, a 7% probability that they would quit. Let's see, did I label that right? Yeah. 7% probability that these people who smoke more than one pack, 7% chance that they may quit. Good. 0.07. And then a 10% probability that they may drop down to a pack or less. So it's 0.1. Now let's see if we can build. The key is building the transition matrix, and basically after that you're done. So we got the non-smokers. We got, I'm just going to just say 1 for 1 or less, and then here, more than 1, I'm just going to say, I need to be country and just say mo. That's how my professor would say. We need mo. So I'm going to be like Dr. Wallace Maryland, Lord bless his soul, who's at eternal rest. So this is non-smoker, that's that first row, 1, and then mo. So this is from, and this is to. So you look at the diagram, you put this together. So from the non-smokers that go to a pack or less, so that's going to 1 or less, that's 0.08. And then the non-smokers who are going to a pack or more, that's throwing me off. I looked over there, it was like mo. What the world is a mo? We're not in the country anymore. So non-smokers to more than one pack, that's 0.04. So this has to be 0.88, because this, you add up these two numbers, you get 0.12. So 1 minus 0.12 is 0.88. Now let's go to, which is the pack or less, And the pack or less, when he goes to the non-smokers, that's 0.1. When the pack or less goes to a pack or more than one pack, that's 0.1. So this has to be 0.8. Now for more than one pack, when he goes to a pack or less, that's 0.1. And then when he goes to the non-smokers, that's the 0.07. Okay. Now we add these two numbers, 0.17. Take that from 1, we get 0.83. Okay. Now the initial setup, well, they tell us directly, right? So we get the initial state. So we got 5,000 people. Of the 10,000 that's polled, 5,000 are non-smokers, 2,500 smoke a pack or less, and then 2,500 smoke more than one pack. So they want us to find part A, what happens within 1 month. So that's x sub 1. So it's this matrix P, .88, 0.1, 0.07, 0.08, 0.8, 0.1, 0.04, 0.1, 0.83, and that's times this matrix here, the initial state, 5,000, 2,500, and then 2,500. Now, and I put that in my graphing calculator, I get 4825, and then 2650, 2525. And I think you know how they go, right? The first number is for the non-smokers. Well, it's right here too. So I was never trained to just write numbers without saying what they represent. So that first number goes with the non-smokers. The second number goes with the people who smoke a pack or less, and that third number goes with more than one pack. Even though the answers are there, I never go by that because I don't trust it. Number two, it's better when you dig yourself. You dig. I think it's in Genesis where when Isaac had to go dig wells because he had to keep moving. Well, that's probably a good sermon there. But I heard one preacher say, dig your own well. So that's all I'm doing is just digging my own well. Now let's look at part B and C. So for this part, it says what happens in 2 months. So this would be x sub 2 would be that transition matrix raised to the second power times what you had for x naught, right? And so that's the 0.88, 0.08, 0.04, 0.1, 0.8, 0.1, 0.07, 0.1, 0.83, that's raised to the second power, times the initial state, again, that was 5,000, 2,500, and 2,500. And don't forget to raise the power. And so when you do that, we get, I got decimal. I got 4687.75, but it said round to the nearest whole number. Let me just write what I had. 2758.5 and then 2553.75. Well, that's not the approximation, that's the exact. And so then rounding to what they want, 46882759, then 2554. And then I think you get it for part C. Watch this. Let me just write up the setup in terms of how you get it. You're looking for just x sub 12. So you take that transition matrix, raise that to the 12th power. You can do that because you're using your calculator. Hello. So when you do that, you get 4,200.7, 3,039.15, and then 2740.15. And then you round to the whole number, so 42213039, then 2740. Okay. So that is that. I'm going to take a pause here, and then we'll come back and talk about the so-called steady state. That's a pretty cool concept, so stick around for that.